All right, oral exam, prompt number 1. Gonna read it out. Imagine you are a sports scientist who is consulting with a high performance coach for a group of elite long distance runners. These athletes compete in ultra marathons that are 50 to 100 miles in length. The coach is wondering why you are having her athletes consume carbohydrates during the race and long distance training. Explain to them how a simple sugar molecule can create energy and fuel repetitive muscle contraction. Be sure to include energy systems and endurance fatigue principles. So I already mapped out my train of thought here just so we can stay on track. But first, let's go over our energy systems. We have 4 of them: anaerobic and aerobic bioenergetics. So the first one, anaerobic, simplest way to produce energy, quickest way, but it'll give you 3 to 5 seconds of energy, so it is not sustainable. But we have phosphagen, or phosphocreatine, plus ADP can be converted or reversed via creatine kinase into ATP and creatine plus energy. It'll give you energy. Fast though, it is not sustainable. Our second anaerobic system is glycolysis. It'll give you about 3 to 5 minutes of energy. Still not sustainable, but it's better. So glycolysis, we start off with glucose, 6-carbon molecule. We have hexokinase, which will then add a phosphate group to the end of it, which will produce glucose 6-phosphate. It'll then get rearranged into fructose 6-phosphate. And then we have fructokinase, which is the enzyme, the rate limiting enzyme. And it's going to add a phosphate group to the opposite end. So it's mirror image. That'll make us make it fructose 1,6-bisphosphate. Then aldolase is going to come into play, and it is going to basically split this molecule into mirror images, into DHAP and into G3P. We have a series of steps that will ultimately give us 2 pyruvate molecules. At this state, a pyruvate can have one of 2 fates. It could either, through LDH enzyme, can turn into lactate plus hydrogen, which can actually then be recycled and can turn back into glucose. Another fate is that it can lose a carbon molecule through carbon dioxide, through breathing it out, and we will make acetyl-CoA, which is the hand step to get into the Krebs cycle. Another way we can get into acetyl-CoA is that we can do beta oxidation from fats, or we could break down ketones to get to acetyl-CoA. But this is when we are going to get into our aerobic systems. We are using oxygen, we're creating carbon dioxide. So Krebs cycle, it is a cycle. Acetyl-CoA has 2 carbon molecules, so that means we get 2 turns in the Krebs cycle. We start off with OAA, which turns to citric acid, and then we have a few series of steps where we turn NAD to NADH, which will produce carbon dioxide. We also have GTP, which will get converted to ATP, and we also have FADH, which will get converted into FADH2. We have 2 turns, so in total, we get 2 ATP, 2 FADH2, and 6 NADHs. And that's the primary goal, is to collect NADH and FADH2. So what are we going to do with these? We're going to go to the electron transport chain, or ETC. NADH is going to go and bind to the first channel. It'll bind its electron and it'll pump out 4 hydrogens. It still has some negativity or charge, so then it's going to go to the second channel and it will also produce 4 hydrogens. Well, it still has some charge, so it's going to go to the third channel and produce 2 hydrogens because it doesn't have as much of a charge. We're also going to get FADH2, and at the second channel we're going to produce 4 hydrogens. It still has some charge. It'll go to the third channel and then it will produce 2 hydrogens. So now that we have those binded and we have all of these hydrogens on the top, what's next to happen? Well, these hydrogens are going to go into this protein channel, and we have ATP synthase. It looks like a propeller, and it's going to convert these molecules, these hydrogens, into ATP. For every 4 hydrogens, we're going to get 1 ATP. So we have 10 NADH, so that will give us 2.5 ATP. And we have 6 FADH2, which will give us 1.5 ATP. So now we've created ATP. That is the best energy system, the most efficient way that we can produce ATP. We can produce energy. So we can go through this whole system again. But wait, these channels are clogged. We have still these negative charges, and we can't bring more negativity in because negative opposes negative. So what are we going to do? We're going to get oxygen because we are in aerobic system. We have that available. So oxygen is going to bind to the 3rd channel, and it'll bind the negative ions, and it will produce metabolic water. That in turn will give us a gradient in the ETC, which will move it down, and it'll clear or give enough so that we can continue and have a gradient to go down so that we can move down. So those are our energy systems. What about muscle contraction? So these are runners. Let's say, obviously, voluntarily running. We want to contract our quadricep voluntarily. So our brain will produce an excitatory impulse to say, I want to contract my quadricep. So neural send out an input, and then it's going to travel down the axons. Well, to travel down the axon, we need to depolarize it. It's going to go down the axon to the synaptic node, right here, synaptic node, and then it gets to the synaptic cleft. It's going to kind of, I think of it like a superpower, like trying to move it with your mind, because it doesn't actually like shoot out, but it goes to the T-tubules, and it's going to send that impulse, electrical impulse, and it's going to go down the T-tubules and also continue to depolarize. Well, next to the T-tubule, we have sarcoplasmic reticulum, or SR, which is full of calcium. So once the depolarization goes down the T-tubule, it'll also do similar to the cleft. It will send its electricity to the SR, and it's going to release the calcium. It'll basically open the floodgates. So what's going to happen to the calcium? It's going to bind to troponin. It's going to go to the sarcomere. It's going to bind to troponin. Troponin is on top of tropomyosin. Tropomyosin is what blocks the active blocking site in actin, because without that, the myosin head would automatically or constantly be bound to it. So without calcium, we can't have this happen because it's going to be blocked. So calcium comes into play, binds to troponin, moves tropomyosin so that it shows the active binding site. Active binding site is exposed. Myosin head is going to immediately bind to it. So we're bound. Now what? To have it move, because we're contracting, this is a sarcomere, so to have this move, we're going to shorten it. That's a contraction. So the myosin head is bound. We're going to need to move it forward. To kind of cock and pivot it, we're going to release inorganic phosphate. And then to do like a power stroke, we're going to release ADP, which is really going to contract it. Well, it's contracted. Now what? You have to let go to recock and pivot and then go forward. So ATP is going to bind to the myosin head to release the cross bridge so that it can rebind. Well, how is it going to rebind? We have ATPase, which is going to break down the ATP that just unbound the cross bridge into organic phosphate and ADP. Well, where did we just hear that? It was from the cock and pivot and the power stroke. So it's just gonna get recycled. So calcium is still present, bound to the site, release inorganic phosphate, cock and pivot, release ADP, do the power stroke, ATP comes in to unbind it, and then it gets broken down. It's going to repivot, and then we're just going to keep doing that until the sarcomere is contracted. Okay, so that's how we get a muscle contraction. Back to the question, why are we having these athletes eat carbohydrates? Well, we know that carbohydrates is easier to burn than fats. Fats is more sustainable. It's similar to aerobic systems, more sustainable, a better energy source. Whereas carbohydrates, it's faster to burn, but that's the problem. It's faster to burn, similar to anaerobic system. It's easy to get to, but it's not sustainable. So why are we having these athletes eat a bunch of carbohydrates? Well, and their endurance. This is endurance training. They're running 50 to 100 miles. Well, we know that endurance training is manipulated by intensity and duration. Obviously, this is going to be a long run. Ultra marathons, they're going to need a lot of energy. So, and because it's high intensity, high duration, we know that the respiratory exchange ratio is also going to be high, which is why I drew this. This is relationship to carbohydrates, and this is relationship to fats. So the increase in intensity, we're going to move more from fats to carbs. And thing being, they are eating more carbs, so that means this line is actually going to be manipulated, and we're going to have a faster crossover from fats to carbs. So we're going to get there sooner. So it'll be better for them for performance. Let me see. And ways that the way our body manipulates or adapts to endurance training is antioxidants. We also do it through increase in capillary density, muscle fiber type switch, and mitochondrial biogenesis. A big one is the muscle type switch. So we know that we always, unless you're detraining or you're old, you switch from type 2 to type 1. Type 2 is fast, easy energy, not sustainable. Type 1 is slow twitch, but is sustainable. It's fatigue resistant. So that is what we want, because the type 1, their ATPase is slower. It's moving at a slower pace, which is what releases the myosin head. But essentially, because it's moving slower, that doesn't mean it's not working as hard. It just means it's going to have much more of a power stroke. So instead of releasing and constantly recocking and pivoting, it's going just to release and then just be able to really turn in and get a bigger power stroke. It's using less energy by having to unbind the cross bridge, using ATP for that. It's more efficient and it's more resistant to energy fatigue. So that is a big reason why we want carbohydrates, is to sustain that so that they're not going to get tired, because they have a long run ahead of them and they're going to need the energy for that. The ATPase, it's more effective energy. I believe that is it for that one. Thank you for coming to my TED Talk.